All right, we've now learned to start working and figure out how to take integrals. And just a note, in calculus, derivatives are, when you're given a problem or function asks to take the derivative, you can almost always take the derivative. I mean, it might get messy and ugly, but there are rules you can do it. Integrals are different. You can't always easily take the integral of a function. There's limitations, there's rules to follow, and in the last section we talked about some of the basic rules for taking integrals. But so for instance, the first problem we're going to do today is the integral of 3x plus 5 raised to the 7th power. I cannot use the power rule here. The power rule is just a variable raised to a numerical exponent. I can't, even though these are added, but it's inside the parentheses, raised to a power. So far as of now, I don't have a way to solve this integral. So then in calculus, we start learning various kinds of rules that help us to start figuring out some of these integrals. So here's one of the first sort of special rules. And it can be a little tricky, and I'm warning you in advance, this is at first can be sort of complicated. Once you do enough of them, you sort of get the hang of it, but sometimes occasionally involves trial and error. You have to have sort of get a knack for it once you do it enough. So I'm going to give you, as we go through some examples, some sort of rules of thumb, and I'm going to give you steps to follow, but this can be at first a little tricky. Now here's one of the first rules. When you have an integral, when you have a bunch of stuff inside parentheses raised to an exponent, it's pretty clear what to do. So this is called integration by substitution. I don't know if you remember back in algebra, you did some problems solving by substitution, and we always like to use the variable u whenever we do this thing called substitution. So what I want to do is I'm going to write down the steps. Let me write down the steps and work out this problem, and then we'll do a couple other examples. So the steps to integrate by substitution for problems like this. The first one is we're going to define, in a sense, you notice what we're going to do. Here's the big picture. Right now, this integral, I've got an x. I'm taking the integral with respect to x. I'm going to eventually convert this problem where instead of x's, it has u's. Because if I do it correctly and am smart about it, when I convert this problem to the new variable u, then I can actually use some of the integral rules I've already learned and take the integral with respect to u. So it's almost like I'm going to convert x to u. When I'm done with this first couple steps, this integral, instead of seeing x's here, you'll see u's there. The reason I do that is because when I convert it to u's, then I can take the integral with respect to u. I will have right now, if I leave it as x's, I don't have any rules to take this integral. I'm going to convert it to u, and I'm going to do it in such a way that when I have my integral written with u's, I can actually follow one of the integral rules I've learned and actually take the integral. So you take the integral, and then the last step, so your integral has been taken, but there's still u's there, so then you convert u back to x, and then you're done. So it's almost like, you know, you're flying to LA and you have to fly through Denver, you know. Flying through Denver is like converting to u. Of course, you finally end up in LA, but you had to go through Denver. I'm going to end up solving this integral, and there's going to be x's in the answer, But in order to get there, I have to go through using these u's. So here are the steps. First, define u. Now for this kind of problem, whenever you have parentheses, or parentheses raised to an exponent, the u is almost always whatever is inside the parentheses. So I'm going to define the variable u to equal 3x plus 5. 3x plus 5 is inside the parentheses. Second step. I'm actually going to now, that u that I just defined, I'm going to take the derivative of this expression with respect to x. So here's u du dx. So I'm going to take the derivative of this with respect to x, right? Pretty straightforward. It's just 3. Right? You remember your derivative rules? Now, and what I've done here, I want to solve or get dx by itself. So in this case, rule of thumb is, because you always have du dx equals this. Easiest quick shortcut is if you just swap these. Whatever's over here goes in the bottom. This dx goes over here, because when you swap them, you end up with this. Although actually what I like to do is when I like the du to be by itself. So you'll see later on where I actually like to write it like this. So I solve for dx. dx equals 1/3 du. Now, replace all your x's with u's. So here's my original integral. Now when I'm done with this step, if it's going to work correctly, I should not have any more x's. I should only have u's in my integral. So 3x plus 5, I'm calling that u. So I can just make this u to the 7th. Now I've got this dx here, but you know what I did just here? I did this little thing where I solved for dx, and it's 1/3 du. So dx becomes 1/3 du. Now if I sort of move these a little bit, matter of fact, I'm going to move the 1/3 all the way outside. So this original integral, I've converted the x's to u's, and now it looks like this. You notice this integral, I don't have any rules. I don't know how to integrate this. But this is the basic power rule. I can actually take the integral of this. Let's just do it. Actually, I should add to the next 5th step then. If it works correctly and you've done the right things, at this point, you should be able to take the integral. Power rule says you add 1 to the exponent, divide by the new exponent, and you also got the plus c here. So really, u to the 8th over 24 plus c. Now, so I've actually taken the integral, which was my goal. I was given an integral, I've taken it. The problem is, the original problem had x's in it. I've taken the integral. My answer is in u's. So what's the last step? Somehow, instead of u's here, I need to convert to x's. And it's pretty straightforward. Because look at, when I first defined my u, I said u is 3x plus 5. Here I've got a u to the 8th. I simply replace that with 3x plus 5. And I've now integrated, I've done the integration. Integral of 3x plus 5 to the 7th dx is this. So this is called integration by substitution. First step, and really the key step, is defining your u, sort of knowing how to define your u, and you go through all these steps, and if it works, then you'll be done. All right. So that's an example where you'll have some problems where you'll have parenthesis raised to an exponent. For that kind of problem, when you define your u, way down here, define your u to be whatever's inside the parentheses. Because this ends up looking sort of like a power rule. But another kind of problem you can have, matter of fact, this is problem number 4 in the book. I don't know if the one I did, that may have been a problem. Nope, I don't see it. Anyways, here's problem number 4. Integral of e to 5x plus 3 dx. So once again, if you remember, I told you when we had rules for natural exponential functions, I said it only works with a number times the variable, and that's it. Very well defined, very strict rules. Here I've got 5x plus 3. The rule I learned about integrating exponential functions does not apply here. So I can't just jump in and use this right away. So I'm going to try and do this u substitution. Now in this case, when you have e to some kind of expression, the first step is to define the u. The best place to start is actually to take that exponent and you call that u. So I'm going to let u equal this exponent, and then you go through the steps, right? If you're looking at your notes, next thing you do is take the integral du dx. Once again, very straightforward. I want to solve for x. I can swap these and put the 1/5 out front. So now I'm ready to substitute. So e to the 5x plus 3 becomes e to the u. The dx is 1/5 du. So if I rewrite this, I bring the 1/5 out front. So now, look what's happened. When I convert my x's to u's, I actually get an integral I have a rule for. This does now fit the rule for integral of an exponential function, because it's really 1 times my variable. So now let's take the integral. 1/5. So you write down, copy down the exponential, divide it by the number in front of the thing, which is just 1. So there's really nothing to write. I have now taken the integral. However, I don't want to leave my answer with a u in it, so now I replace the u. I go back and I say, well, my u was 5x plus 3. And I've now taken the integral. All right, let's do a few more examples. They can get a little tricky. Sometimes you just have to work through these and a little trial and error sometimes. Problem 6. 1 over 3x plus 5. They have something like this. It's pretty obvious. I mean, at some point, you don't have any choice. If I don't have any rules to do the integral like it is. So I'm saying, well, obviously this is a section, integration by substitution. I probably should use substitution. What should I make u? Well, obviously, hopefully you would say, well, let's try and make it all this stuff into the denominator. Actually, let's Let me do off to the side. I keep forgetting to do that. Take the derivative with respect to x. Solve for dx. Now go back over here. Switch from x's to u's. So 1 over u, then dx, is 1/3 du. I'll move this 1/3 out front. Now hopefully you've been doing integrals enough where you would notice that this is actually an integral that we can solve or we can work out. Hope you realize it's that special case when you have 1 over a variable by itself. Remember, that's the case where the integral is actually the natural log of the absolute value. So I've still got the u. I want to get back to x. U was 3x plus 5. And there we are. We have integrated it. All right, let's do a couple more, just because if you see enough of these, then when you do them on your own, hopefully you can figure them out. How about number 8? The integral of x minus 1 to the 5th plus 3x minus 1 squared plus 5 with respect to x. So here's a case where we have some parentheses, right, some exponent, and you notice it's the same stuff inside the parentheses. So hopefully you say to yourself, well, the best place to start would probably just let u equal x minus 1. Now just so you know, the way I do it here probably is not the way the book does it. Sometimes I come up with a way that to me seems simpler and hopefully easier for students to understand. So if you like the way the book does it, fine, but this is the way that makes sense to me. Now I solve for dx. In this case, actually, dx equals du. So now, if I do my substitution, x minus 1 to the 5th, x minus 1 u, so this is like u to the 5th. 3 times x minus 1 squared, x minus 1 is u, so 3 times u squared plus 5 times dx. You know what this is? This is pretty straightforward. This is like, both of these are straightforward power rule, and this is just a constant. So this is u to the 6th over 6 plus 3 u to the 3rd over 3. Whoops. I forgot to change the dx to du. Plus 5u plus c. And the last step is, every place you have a u, put in x minus 1. X minus 1 to the 6th over 6 plus 3 x minus 1 to the 3rd over 3. Those actually cancel. Plus 5 x minus 1 plus c. That one actually wasn't too bad. All right, let's do a couple more. Practice makes perfect. Number 10. Integral of 2x e to the x squared minus 1 dx. All right. Now this is a good one because this gets it's a new twist in this one. So I look and I've got 2 here, but I got this x here and this e to the x squared minus 1. So I say, well, what do I want? What should I let u be this whole thing or part of this? Once again, this is a case where if you do these enough, you sort of see what you probably should do. And this case is because I got this exponential, when we did that problem a while ago, we had exponential. I made u equal to the stuff in the exponent. I'm going to try that again and see if it looks like it's going to work. So now I take the derivative, du dx. Turns out this is 2x. Now if I want to solve for dx, once again, you can sort of swap those. Turns out this is a little interesting because dx equals 1 over 2x times du. So you have x's and u's here both, which is a little strange. But let's see what happens. So now I'm going to try and convert from x's to u's. Move the 2 out front. Now here's a problem because first thing I have here is an x. So I somehow want to rewrite that like with a u somehow. But I look over here, my u is x squared minus 1. I don't know what to do with this x. Here's what you do. In this case, for now, you leave the x. And then I'll say, like, we cross our fingers and hope somehow the x takes care of itself. But I cannot eventually have an x in the integral. I have to have this be all u's. Because I'm sort of stuck, let's put it in here for now, and let's sort of cross our fingers and hope something works out. And you'll see, in fact, something does work out. So for now, we're trying to get rid of x's, but we're sort of stuck with this one. Let's leave it for now, and let's see what happens. E to the x squared minus 1, well, that becomes e to the u. We've got dx. So this whole thing, I'm going to substitute in for dx. So I got 1 over 2x du. Now the same thing. I'm trying to get to all u's, and I've actually brought another x in here. So it's like, this doesn't look good because I'm trying to get all to u's, and I've got x's. But then you look, and hopefully the light switches on, and you say, well, I've got this x here, and I've got this x here, but this is in the top, and this is in the bottom, and you know what happens? They actually cancel out. And maybe I'll even bring this 1/2 out front. As it turns out, God is good, and these things did cancel out, and I am left with an integral with only u's, and beyond that, it's an integral I have a rule for. E to the u du is just e to the u plus c. Now, I get rid of my u by substituting x squared minus 1. And lo and behold, we were able to integrate it. So that's the kind of thing you start to see now, where sometimes it looks like you're not really making progress because you have x's, but just ride with it for a while, and oftentimes the x's will end up canceling out, and then you're making progress after all. All right, maybe 1 or 2 more. Let's see what I've planned. So here's 24. The integral of 1 over x times natural log of x. So once again, it's not always maybe at first clear what to do. I've got an x here, natural log of x. What should I make u equal to? Maybe x? I mean, you can try that, but if you set u equal to x, you'd have 1 over u times natural log u. You can try it, but I think you get stuck again. Let's see what happens if we make this natural log of x equal to u. Now you have to go back. Remember what the derivative of natural log of x is. Check your notes if you forget. Remember, it's just 1 over x times the derivative of what's inside, so it's just 1 over x. If I solve for dx here, do the algebra, it's actually x times du. The x is in the top here because it's in the bottom over here. So now, let's see if I substitute, and it looks like I'm making progress. So once again, this x I'm going to stick in for now. I'm sort of stuck with it. Natural log of x is u. Dx is x du. And now, lo and behold, good things are happening because I have an x here and an x here which cancel out. One over u du. I know how to integrate that. Now be careful, it's not the power rule. This is that special case where it's a natural log of u. U is natural log of x, so in a strange way, this looks sort of bizarre, the natural log of the absolute value of the natural log of x plus c. Looks strange, but that's actually the answer. All right, so those are the kinds of problems that you're going to have. Now let me do one more section. You're going to be assigned, I'm going to do problem 38. Let me read the instructions. 38 says, solve the given initial value problem for y equals f of x. So I think they're doing what we did a little bit ago. They give us, in this case, they give us a derivative. They write it as dy dx. So they give us a derivative. And they say y equals 3 when x equals 1. So basically, they're basically giving us a point like 1, 3, right? And they're really wanting to know once again, when you integrate the derivative, in this case, you get back your function, which we can also call y. So basically, we're going to take the integral of this and try and come up with our original equation, our original function. So this becomes a problem of what's the integral of square root of 4x plus 5. Of course, I'm not going to leave it like that. How I integrate that? That actually looks like a good candidate for substitution. See if I can squeeze it in over here. Let u equal 4x plus 5, right? So I got stuff inside parentheses raised to an exponent. That's what I'm going to try and make my u. Take the integral du dx is 4. Dx is 1/4 du. So switch to u's. U to the 1/2 times 1/4 du. Use the power rule. 1/4 add 1 u to the 3/2 divided by the new exponent. So the 3/2 becomes 2/3. So it's like 2 over 12. I believe it's 1/6. Switch back to x's. 1/6 4x plus 5 to the 3/2 plus c. Now what they do is, when they give us this point, we've done this before, this gives us a way to calculate the c. So really what I have here now is And I'm going to check my notes, make sure I haven't messed up on the math. Yep, looks like I'm good. I'm going to plug that point in for the x and the y, and that allows me to calculate the c. Let me get some more paper here. So y is 3 and x is 1. So y is 3, x is 1. So really, so this is 9. Now this is a case where to figure this out, I'm going to actually convert this back. I'm going to figure out what 9 to the 3 halves equals. If you remember your algebra, I'm going to actually convert this back now. Square root of 9, and I'm going to write it like this. Nine to the 3 halves is really 27. So I have 3 equals 1 over 6 times 27 plus c. So this is like some algebra. C equals 3 minus 27 over 6. Get a common denominator. All of that to finally, that's what C is. So now I go back here. I can plug that in. So y equals 1/6 4x plus 5 to the 3 halves minus 3 halves. All right, that was sort of fun. So that is integration by substitution. Hopefully once you do that enough, you get the hang of it and it won't be too bad.